All right. Hello, everybody. Hello, HCI people. Welcome to Comp 3430 Operating Systems. Today, we're going to start moving on to a different topic. And today, the topic we're going to be starting to take a look at is threads. So we have been doing concurrency for quite a while with the processes stuff that we've been working on. But I mean, the main problem that we've got with processes is that in order for us to have these processes be able to talk to each other, we've had to establish these pretty complicated mechanisms for processes to be able to talk to each other. So we've got signals and we can send messages between processes, but they're pretty limited in what they can communicate. We've started up with pipes, and pipes give us the ability to send more information. And they've also added a couple of new concepts, like we've got this idea of synchronization between processes. We've got this ability to set up, we've got this ability to set up stuff so that we can send messages between these two processes, but read specifically will block, and it's going to wait until there's actually something in this queue structure for us to get something from. Synchronization is going to continue to be important as we move into threads, but the big thing about threads is that we're going to be able to take away a lot of the stuff that we had to build up for processes. The big idea with threads is that rather than duplicating the address space, when we duplicate our process control block, we're going to have different units of concurrency, different things that are operating at the same time, but they're operating within the same address space. And this takes away a lot of the complexity of things like having to set up pipes and having to send signals between things, because now if we are sharing the same address space, we can actually just talk to each other with variable changes. So what I want us to be able to do by the end of today's lecture is I want you to be able to compare and contrast processes, threads, and then there's this word applications here. I want to be clear about what I mean by the word applications here. When I think about an application, it is Firefox. That is one application that I have on my system. This uses processes and threads together in terms of trying to accomplish the task that it's trying to accomplish. The other way that I want us to think about the word applications is the inert file on disk that represents our compiled code. This is just something that's laying on disk and not actually doing anything. I want us to be able to compare and contrast processes. So I want you to be able to talk about how they're similar to each other and how they're different from each other. And the exercise, one of the exercises that we're going to do today is to take a process-based piece of code and translate that into threaded code. I want you to be able to write code that uses library calls to create and manage threads. In this class, for exercises in class, we're going to be using a library that's called pthreads. Pthreads is a library to do threading, but it's not the only library to do threading. When you're starting to work on assignment 3, and it seems like a long way off, because we're still working on assignment 2, but when we're working on assignment 3, we're going to be implementing our own threading library. We're going to build up our own threads using some of the supports that we have in the operating system. But for exercises that we're doing in class, for simplicity's sake, we're going to be using pthreads. And so I want you to be able to use pthreads to create threads of execution, and I want you to be able to use pthreads to manage threads. So to be able to do things like control what code they're actually running, and to do synchronization things with them. This is a continuing learning outcome, and we've been kind of working on this together as soon as we started talking about processes. I want you to be able to describe the operating system data structures needed to manage a process and those needed to manage a thread. I copied and pasted this from last term, and I recognized that I added that extra D last term, and I said, wow, I should delete that. And then I just never did. I never did. We should be able to manage a thread, not manage a thread. We should be able to manage a thread. We've started with this in terms of thinking about things like the process control block. We've started to think about this thing in terms of things like the open file table to represent the state of our process. We're going to be taking a look at an actual process control block. In our textbook, we've got process control blocks that are structures. They're structs that are defined for the XV6 operating system. And this is a more, it's a Linux or Unix-like operating system that's for teaching and learning. Today, what I want to do is I want to spend some time actually taking a look at Linux kernel source code. So I want to take a look at the actual process control block for the Linux kernel. And I want to spend a little bit of time thinking about how the threading library that we're using, pthreads, is interacting with our operating system to be able to start these different threads of execution. One of the things that we are going to find out today that's maybe a little bit of a surprise is that we've been using threads the whole time. We have been using threads as soon as we started doing processes. There's always a thread of execution in our process, and we'll think a little bit more about that as we get to it, but there's always at least one thread of execution in our process. Time permitting, but more likely this is going to happen tomorrow. The next task that I want to do is to start spending some time thinking about problems that we're going to encounter as we begin to work with threads. What's really nice about threads is that we share an address space. We don't have to have these complicated communication mechanisms like pipes and signals. We don't have to ask the OS to do a bunch of stuff for us because we can just change variables in our own address space. The problem with that is that when we've got multiple threads of execution trying to update the same value in the same virtual address space, we can run into situations where we lose things. We lose updates. We are going to get into a state where we're going to try to increment a value and it's just not going to work, or at least it won't appear to work correctly. So I want us to be able to start thinking about running code concurrently and identifying critical sections. So what are the fragments of code that would or would not work correctly if it were executed concurrently with multiple threads? And then, once we've identified that, begin to try and protect that critical section using a locking mechanism. Locks here are going to be one of the ways that we're going to do synchronization with threads. Processes, they kind of have locks. We could kind of think about files as locks. We can use locks at the operating system level in Linux. We're not going to do any of that stuff. Synchronization for us for processes is pretty much limited to read blocks and wait blocks. With threads, we're going to have another mechanism to do synchronization to make sure that multiple pieces of code do not enter the same piece of code at the same time. And so we're going to use this, this mutex lock structure to be able to accomplish that. So first and foremost, I want to first kind of give you a brief introduction to the idea of what threads are. And then what I want to do is I want to spend some time taking some code that is already written for processes and translate that to using threads instead. So what we've been working with so far are processes, and traditionally these are considered to be heavyweight or coarse-grained concurrency. Does everybody know what the word coarse-grained here means? So coarse-grained, for clarity here, coarse-grained versus fine-grained or granular, the granularity of something. I want you to imagine in your mind's eye right now that you are on a beach, because that's the best place to be on a day like today. We're on a beach somewhere. Coarse-grained are like big rocks. You look out on the beach and you see that there's really big rocks everywhere. Boulders even. Fine-grained, and this is what we're going to be thinking about, again, traditionally in terms of what these two different ideas are. Fine-grained means like sand. The sand is really, really small, tiny, tiny pieces of the same big thing. So coarse-grained is really, really big units. They're heavyweight. They've got lots of extra stuff attached to them. Fine-grained is it's going to cost a lot less. It's going to weigh a lot less. It's going to be just much, much smaller. Is that okay for you? Okay, awesome, good. So traditionally, and I want to emphasize this traditionally, processes are considered to be heavyweight or coarse-grained concurrency. And I want, think about this for a second. When we do this fork process, we are duplicating our process control block. We're duplicating our process control block, and that includes things like duplicating our virtual address space, so that when I make changes to variables in my first process, it doesn't actually affect the variables or values in the other process. This seems like it's pretty heavyweight compared to what we're going to accomplish with threads, which is I'm going to launch a new task inside the same virtual address space. And it's going to have much fewer kinds of things that are attached to it. So as opposed to being an entire process, we're going to have something that's just a fragment of what a process is. And I'm going to have that fragment of a process running code inside the same address space as what I've got as I initially started. I want to start here by taking some code that's using processes right now and changing this to use threads. So I invite you to follow along with me if you want. The repository that I'm going to be working from is this one. It's the regular group that we've got in GitLab, and then the project or repository itself is called Thread Management. I've linked to it in today's lecture notes on the course webpage. So if you want to follow along there, you can clone the repository to your local system or to Aviary. This is something that, for clarity, should work on Mac OS as well as it does on Linux. So you shouldn't have to use Linux for this one. So I've already got this repository here. I'm going to clean it. And there's a few different sets of things that we've got here. There's a file that's called processes.c. This is the one that we're going to take a look at. I want to see what it does right now with processes. I want to run it and observe what its output is. There's a make file that builds everything. There's a README that describes everything. There's a folder here that's called critical sections. And critical sections itself contains a bunch of examples of code that we're going to take a look at later. But for now, we're going to focus on this processes.c code fragment. So I'm going to walk us through this code and approximately what it does. The very first thing that we've got in this main function, and I'm just going to quickly ask, is this big enough for you in the back? Yes, awesome. Okay, thank you. The very first thing that we're doing here is we're getting a value from keyboard input. I'm getting exactly one character, and I want exactly one character from this. So I'm using getchar here, and I'm saying just type in a letter and press Control D. I don't want to press new line here. I just want to flush that single character into whatever variable that I've got here. After I get that input, I'm going to fork. I'm going to duplicate our process control block, including our open file table. And then at that point, I'm going to do two different things based on which branch we're in. So whether we're in the parent or the child of this process group. In the child, I'm going to ask for another variable or another value. So enter another letter, press Control D, flush standard input, get that thing, print out a new line character. And in the parent, I'm going to just wait for the child process. After these two branches are done, I'm printing out what the value of this variable is at the time that we're exiting this. And both of our processes are going to try to print this at approximately the same times in terms of when they're finishing. So our parent process is going to block here on wait, and our child process is going to block here on getchar. As soon as I enter something, they will both effectively become unblocked because the child process will finish, the parent process will become unblocked, and the parent process will print out that message. The goal here, again, similar to what we were doing with the very first exercise that we did with processes, is let's show that these address spaces are not shared with these two different processes that we've got here. So I'm going to pop open another terminal to my side. I'm going to go to today's lecture here. I'm going to make this, and I'm going to run it. And somebody shout out a good letter. L. Okay, so L is the first one. What's the second best letter? X, thank you. Okay, so in our parent process, we loaded that initial variable, that initial value of L. This is our parent process's process ID. It never changes. Our child gets that input. We are getting some more input here from the child process. It's changing its own value of this file scope variable that's called C, which has been declared up here at the top. It's changing it, and when it prints out that same message, it's X. So what we've seen so far with processes, this should logically make sense at this point. This should all make sense in terms of like the two processes don't actually change each other's virtual memory. We want to start taking this code and changing it to use pthreads. And so the first thing that we're going to need to do is we're going to need to make a new thread of execution in our code. The function that we're going to use for that is called pthread create. I'm going to zoom in on this manual page, and I'm going to expand this so that we can see it a little bit more clearly. Where fork duplicates our process control block, the idea that we have with pthread create is that it's going to add a new thread of execution to our process. So in the idea that we have this task list that has multiple tasks at the operating system level, what we're doing right now is instead of making an entire new process control block, we're adding just a new thread of execution to the same process control block. Pthread create takes a few different arguments. The first is a pointer to this pthread type. This is an object that we're going to use to keep track of this thread of execution. Internally, we don't know or care what's inside a pthread. It's not really that important to us. It's just a way for us to identify a thread of execution within a process. With processes, we had the process ID. And the process ID was the way that we could decide which process we're going to send the signal to, which one we're going to try to terminate using something like the interrupt signal. The second argument here is one that we're basically just going to ignore, but we can also specify some attributes about the pthread when it's launched. When I am using pthread create, I will almost always pass null to this. I'm not going to put anything in here because I don't want to change any of the behavior of the pthread right now. The last two arguments are about what we're asking the pthread itself to do. So when this thread of execution is started, we're not going to be going to the same line of code that we were in before. Instead, what we're going to be saying is, when this thread of execution starts, I want it to start in that function. This is a function pointer that we're passing here, and the function pointer has a signature of, it takes as one argument a pointer to void. So this is just a pointer to something, and we internally have to know what that thing is. We'll take a look at working with arguments in pthreads a little bit later. The other thing that this returns is a void pointer. It returns a pointer to something. The last argument is what I want to put in the arguments that are passed to the function when it's invoked. When I create a pthread, I'm not starting my main function. I'm going to say, here is the function that I want you to start running in. That means that in terms of the stack that this thread of execution will have, is it's just going to be at that function immediately. That's the bottom of the stack for this thing. We're not ever going to come back to main from this function. We're just in that function. So let's take a look at using this. The very first thing that I want to do is I want to take some of the stuff that's in my main function here for the child process, and I want to put that into a function. With my main function with processes, what I was trying to do ultimately was, let's make a new process control block. They both have the same stack. They both have the same program counter, so they're both going to move to the next instruction at the same time. But now I'm going to ask for a different thread of execution to start. So I'm actually going to quit processes.c. I'm going to copy processes.c to threads.c so that I can have both at the same time. And the first thing I'll do is this: void pointer child thread task. I'm going to call this child thread task. This is the function that I want the thread to invoke. This is the function I want the thread to start operating in. And this takes as an argument a void pointer. When this function is compiled, I'm not going to do anything with this argument yet. So I'm going to cast this to void to say I'm not using this. I want to suppress the warning that this is an unused variable. What I want this thread of execution to do is what the child process currently does. So I'm going to cut and paste these lines. And the other thing that I want to copy is that the behavior of a thread when it's in this function is that it never returns to the main function. This is never going to go back to the bottom of main because in terms of the way that this thread is executing, that's the only function that's on the stack. When we return, there's nothing left to pop off. I can't go back to the main function because there's nothing left to pop off here. So I'm going to copy this very last line here. So that's line 46 right now in my code. I'm going to paste that here. I'm going to write it. And the very last thing I want to add to this function is that we got to return something, but I'm not returning anything. So I'm just going to return null from this. Now that I've got this function, I want to actually start a thread running that code for me. And so I'm going to use pthread create, and I'm going to replace fork with pthread create. I'm going to change this comment, start a new thread of execution within this process. So pthread create. The first argument that I have to pass here is a reference to one of these pthread type objects. And so I'm going to declare one of these. I'm going to replace pid_t child pid with pthread_t threads to pass a reference to that, so a pointer here. The second argument, like I said, I'm just going to pass null. This is a way that I can change some behavior of the way that the thread itself works, but I'm just going to pass null because I don't want to do that right now. The third is going to be the function that I actually want it to invoke. So I'm going to pass child thread task here. And the very last thing that I pass to pthread create are the arguments that I want to pass to this function. And I don't want to pass any arguments to this function right now, so I will also put null here. After this line, that new thread of execution has started. So after that line, there are two threads of execution in this program right now. There's two threads of execution in the process. The main thread of execution, this is the one that gets started when our process starts. So this is what's running code in main initially. Main thread of execution is the one that calls pthread create. The result is that there is a new thread that's created, a new thread of execution that starts running in this argument. And the main thread of execution will return back to this point. So we're just going to keep on running in the main thread of execution. But there's two different things happening at the same time here. After I've launched the main thread of execution and a new thread of execution, After I've launched that, then I'm going to take the parent branch of this conditional statement that we had before. So I'm going to delete lines 41 through 45 here. And I no longer have a conditional statement in my main program here. I don't have conditional statement in main at all anymore. I'm going to print out that I'm waiting for this child to finish. But I can't just wait here anymore. Wait is explicitly saying, I want to wait for a child process that I've launched. But when I create this new thread of execution, it's not a child process, so I can't wait for that. Instead, what I'm going to do is I'm going to have to call a different function. The function that I need to call here is called pthreadJoin. Semantically, this is the same thing as wait in terms of processes. The first argument is kind of weirdly not a pointer to the object. It's just the object itself. So we're not passing a reference to this thing, we're passing the thing itself. The second argument is a way that we can get some information back from the function's execution. So some information back from that return statement. I'm going to ignore that for now. I don't want to get anything back from this, so I'm going to pass null to this option here. So I'm going to say pthreadJoin. The first argument is just thread, not ampersand thread, just thread. The second argument is null. I don't want to accept any return value from that function. Once that's done, once that thread of execution is finished, then I still do want to print out that last statement. I want to print out that message that says the value of this variable is this value. The last thing I'm going to need to do to this to make it complete is I did not include pthread.h yet, so I'm going to add that to the top. So I'm going to go back up to the top of my function, to my file here, number include pthread.h. And the other thing that I'm going to need to do is I'm going to have to change my makefile a little bit. This line right here is telling us that in order for this to compile, you're going to have to add this extra library option to your compile command. So let's take a look at our makefile and we'll add that. I'm going to quit the manual page. Whoops. I'm going to quit the manual page. I'm going to open up my makefile. And on here, I've actually already got this. So I've added this line ld_libs is equal to -l pthread. So this is the line that you need to add specifically for pthread support. And I want to add threads to this. So I made this new file that's called threads. So I want to add threads to my all and to my clean. I'm going to quit this. I'm going to make it. And I'm going to run this. I should probably change this to not say before fork, but instead before pthread create. I'm going to hit Control D. I'm going to make this, and I'm going to run it again. OK. Before pthread create. I want you to mentally step through this right now. I want you to take 3 seconds, and I want you to start at the main function here. This is our first line of output. This is where we're getting input here. We are currently blocked on this line right now. I want you to think about what your expected output from this program is in the state that it's in right now. So just take 3 seconds to do that. Okay. So now I need 2 new letters. M, Control D. Okay, so we're in the parent waiting for the child. The main thread of execution is blocked right here right now. The new thread of execution that we created is blocked here right now. So what's another letter that we can type in here? I don't think I can type that. Oh. And then I'm going to hit Control D. There's 2 interesting things here. One is that all of these messages have the same PID. All of them have the same process ID. Every single message has the same process ID. The relationship that we have here between threads of execution and processes is that a process has 1 or more threads of execution. In this code right here, we start with 1 thread of execution, our main thread of execution. When we get to line 37, after that succeeds, we have 2 distinct threads of execution. And after pthread join on line 46 down here, we're back down to 1 thread of execution. The other interesting thing is that both of these messages here, the last 2 lines that we've got, the value of C is, they're both O. They're both the second value that we entered. And this is different from what we had with processes. So if I do the same thing, if I do the same thing, M, Control D, O, Control D, we get 2 different letters here. These are 2 different processes. They have different address spaces. When I make changes to the variables in one process, it's not affecting the variables in the other process. When I do the same thing here with threads, M, O, these 2 threads of execution are in the same process. They are in the same address space. So when I make changes to something that's in the shared address space, I'm making changes to the shared address space for both of these different tasks, both of these different threads of execution. How are we doing with this? Is this okay so far? Any questions? The first place that I'm doing it is up here in child thread task. So that's this line right here. The second place that I'm doing it is at the bottom of the main function. Way down here. Yeah. Sorry if it was cut off on the bottom of the screen. After that point, we're back down to 1 thread of execution. The effect is mostly the same. We've got 2 different things that are running at the same time. We're synchronizing both of them. The way that we're synchronizing them is a little bit different than what we've done before. Pthread join here, the only way for us to wait for a task to finish is to wait for a specific task. There's no obvious way that I'm aware of to wait for any thread of execution to stop. The only way we can wait for a thread of execution to finish is to wait for a specific thread of execution to finish, as opposed to just wait null, wait for any child to finish. So this is more synonymous with wait PID. Synonymous with wait PID. This is closer to what wait PID does as opposed to wait passing a value of null to this. But the effect is the same, and the main difference, the primary difference here, is that we're operating within the same address space as opposed to operating within two distinct address spaces. So this is pretty cool. This is pretty cool because now our different threads of execution can just talk, they can just talk to each other directly. If I want to, as an example, send a signal between one thread of execution and another, I just have to change variables values. I don't have to send a signal. Here's one way I can do that. One way I can do that is I'm going to make another file scope variable here that's called flag. I'm going to set the value to be 0 for now. It's unset. In my main thread of execution, after I've created this new thread of execution, I'm going to block while flag is equal to 0. Block, spin, wait until the flag is set. To set the flag in the new thread of execution that I've created, I just say flag is equal to 1. I don't have to send signals because we're making changes to the same shared address space. These two threads of execution are operating in that same shared address space, so I can communicate between these threads of execution this way. I kind of want to see what our OS is starting to do underneath and what we're starting to ask our OS to do underneath. So my next task, the next thing that I want to do here is I want to take these two programs that we've got now, one that's using processes and one that's using threads, and I want to see how the interaction between our code and the operating system is changing using this strace program. So I'm going to pop back to my terminal. I'm going to make this one last time. And now I've got processes and threads. And I want to run strace to run both of these different programs. I'm going to quit threads for now. And I'm going to run strace on both sides here, one for processes and one for threads. Processes is going to be on my left side and threads is going to be on my right side. I want to see the output from strace by following forks. I want it to follow the forks and print out the system calls that each of the different processes are making. So I'm going to say follow forks. I'm going to do filtering like we did last time. I want to do filtering on file descriptors, processes, and files. And I want to run threads on this side. Processes, I think I said. And on this side, I'm going to do the same thing. strace, follow forks. Actually, I'm going to change this slightly. I'm sorry. I just want processes. That's all I really want. So I'm going to filter just on process. trace is equal to %process, and I want to run threads on this side. I'm going to hit enter on both of these lines. The first line of output here is coming from our shell. It's coming from our shell. It's coming from our shell. It's coming from our shell. The first line of output is coming from fish. The first line of output is fish is launching execve. It's asking the OS to start these programs that I've just asked it to start. Now we're blocked in both of them, waiting for input. In both of these cases, this is before we've caused a new task to be created. We haven't made a new PCB yet with fork, and we haven't made a new thread of execution yet with pthread create. So I'm going to enter a letter here. I'll do F for Franklin and F for Franklin. And I'm going to hit Control D on both of these. Control D and Control D. In both cases, I'm creating threads here, and I'm creating processes here. In both cases, the actual underlying system call that I'm making on Linux, I want to be clear that this is on Linux, is clone. We're going to take a look at this in a moment, but on Linux, processes are threads, and threads are processes. The difference is that processes, when we call clone here, do not share an address space. Each of these tasks that are being created will get their own independent address space. And when we're working with threads here, what we're doing is ultimately, and the important parts here are these complicated flags that are being passed to this. We don't care what they actually mean. To be clear, we don't care what they actually mean, but the difference here is one of them says, don't clone the address space. Just make a new task and point them at the same address space. There's another couple of interesting differences. One is that with processes, it says child stack is equal to null. And with threads, it's pointing our stack at an address. When we create a new process, with fork, we're duplicating our PCB and we're duplicating the stack. We're setting the program counter to the same location in both of them. And so the stack is effectively going to be the same for both of those different processes. With pthread create, we're saying, I want you to start running in this function, and that's the bottom of your stack. We need to make a new stack for this thing. It has to have its own stack. It has to have its own stack so that when it starts to run functions, it's not going to clobber the main thread of execution stack. In both of these cases right now, in our parent process or the main thread of execution, we're blocked. We're waiting for the child or the new thread of execution to finish. With processes, it's actually called wait. With threads, there is no process management system call here that's being made. We are blocked. We're not doing anything. We are not going to proceed until this thread of execution finishes, but we're not doing a process management system call here. I'm going to enter another letter. So I'll do B for Bristow and hit Control D, and I'll do B for Bristow and hit Control D. With threads, the next process-related system call is just exit. Like, this program is done now. It has no more threads of execution, so let's just finish up. With processes, our wait system call is resuming, and then there's also a signal that's being sent to the parent process that says that the child has exited. So that's part of the relationship between these two things with the wait system call here. So on Linux, and I want to emphasize that this is a Linux-specific thing, the system call that we're actually invoking underneath for both pthread create and for fork is the same system call. We're accomplishing ultimately the same task. Yeah.
Kind of different though. One is clone 3.
Well, sure. One is clone 3. Clone 3 here is defined as not actually having a glibc wrapper. So that part here provides no wrapper for clone 3. That means glibc is our standard library. That means that glibc is actually invoking a system call directly. We could do that. We could make a system call directly using this syscall mechanism, but I don't want to do that. Ultimately, though, the arguments are similar to what we have with clone, but they're different. You're right, they're technically different, but the mechanism underneath is ultimately the same mechanism. Yeah.
So far, and goes to full function. So in processes, we exit when we call exit or return something.
Yeah.
While in threads, it's the same thing. Like, or, yeah. Am I getting that right?
With threads, it's when we return from this.
What happens if there's no return state?
I don't know if we'll be able to compile this code because there's a required return type for the signature that we pass to pthread create. The other thing that you just said is that we exit when we exit. So what happens here if I call exit from my thread? So I'll run this. Right now, we're blocked here in our main thread of execution. Take a moment, predict what you think the output is going to be. When we had this before, there were 2 lines of output that were the same. They both said the value of C is whatever the letter is. I'm going to enter a letter that will unblock from this line. We will start our new thread of execution, G. The parent is blocked here. It's waiting for our thread to finish. And our thread is blocked here, waiting for us to enter another letter. So I'm in a process. I'm in the same process. There are 2 threads of execution, and I'm in the same process. When I call exit, I'm saying this process is done. It doesn't matter how many threads of execution there are. We're all done. Everybody's done now. We're going to exit. I'm going to take that line out because I don't want that to happen right now. I'll comment it out, and I'll put a comment above this that says this causes the entire process to exit, even though we're running this a new thread that we added after the process initially started. This is going to cause the entire process to exit. And so there's only going to be one of these print statements that comes out. The print statement that comes out is the one that we printed in our thread. The main thread of execution here, even though it was stuck waiting, it never gets to finish what it's doing because we've invoked this exit system call. I'm going to come to you in just a second. When we normally just return from this, we're taking that last thing off the stack for that thread of execution, and that thread of execution is removed from the process. It's no longer there to be running, and it's just the main thread of execution that takes over again.
So when the stack is done, it's done.
Within a thread, when the stack is done, it's done itself. Yes. Yeah. Yeah. So the question is about returning stuff from pthreads here. And are we only going to be able to get it when we call pthread join? Do I understand you correctly? Does it matter when we call pthread join? Okay, so in this, I think I see what you're saying here. In the same way that if you call write to a pipe and then later, some like much later time call read, that data is still going to be there. After this has ended, and if I just spin around here and sleep for 10 seconds and don't do anything, then we'll still be able to get the return value. However, I want to make a point about what part of what your question was with relation to pipes. When we've got threads of execution like this, we don't even really need pipes. We just have a queue. We just build a queue and we enqueue things in the main thread of execution and we dequeue things in the other thread of execution. We don't have to have pipes at all because we're both sharing the same address space, so we can just work with the same data structures that we've got. Yeah. Any other questions? Yeah.
creates in the same as V, like doing just that one process control block for the whole process?
So the stack itself is going to be in a structure that's called the thread control block. A process control block will have one or more thread control blocks within it, and each thread control block will have its own context, and they will each have their own stack pointers. So every thread of execution will get its own stack. And so if we're thinking about the address space that we've thought about kind of traditionally of code, heap, stack at the bottom, we no longer just have one stack at the bottom. We might have several stacks that are kind of scattered throughout the address space as opposed to just the one at the bottom. Yeah.
Is there any way to check on the status of the thread with this?
The status of it, like, is it still running?
Yeah.
I don't know if there's a pthread function, but we're operating within the same address space. So if we want to indicate progress to something, one way that we could do that is from this, I can say flag equals 1, flag equals 2, flag equals 3, and kind of continually change this variable that says this is what my current state is. And because these two threads are running in the same address space, the main thread of execution can just ask the question, what is the current value of this flag variable? And I can keep track of progress in a way that I couldn't with processes, but I'm not sure that there's a specific function that I can call for that within pthreads. If I'm understanding your question correctly?
Yeah. How do you know that thread would never act on this? Like, if you start exact inside of a thread, what happens? Like, when you start mixing it.
Okay, that is an excellent question. So how do you know that a thread doesn't operate maliciously? And then I'm going to follow that up with what happens if you call exec inside of a thread. I actually don't know what happens if you call exec within a thread, but I'm going to guess the same side effect as what happens with a process, which is that we just have a new code section running. And so I don't know, I just want to try it. I want to see what happens. So what happens if I call exec here, let's just do exec v, and I'm going to pass to this, so yes, this is yes. This is the program that we were seeing on the test there. Yes is at user bin yes. And the arguments that I want to pass to this are going to be arg0 is going to be the name of the program. Yes. And I don't want to pass any other arguments, so it's null as the second argument here. And I got to put a semicolon at the end of that line. Okay. I'm going to run threads. I'm going to enter K, and now I'm in the child. We're blocked right now on this line in that new thread of execution that we've launched. I'm going to hit S. And now we've replaced our entire code section with a different program. And so our main thread of execution is gone. It's not there anymore. There's nothing for us to continue operating with in this case, because we've completely replaced our code section with this new program. How do I know that this thread is not going to act maliciously? With threads, you wrote the thread. You wrote the function that's being invoked by the thread. And so that's kind of how you know that it's not going to act maliciously, is that you wrote it. And so unless you're writing it to act maliciously, then it's not going to act maliciously, which is different than calling exec. You don't really know what that program's going to do when you call exec. It's just going to do something. I'm going to also comment this out, because this also causes our program to do stuff that we don't really want it to do right now. Did I understand your question correctly? Okay.
Which then, what your subthread though is responsible for working on
how does this parent thread know that everything is still okay underneath?
You're asking questions that I've never thought of before. And so I don't actually know what's going to happen if I do fork here. I mean, I think that we're going to have two processes that have two threads running, and then they will both immediately stop because this program, sorry, I jumped to the bottom there. This process is now finished after we return from this statement. But I don't think I want to investigate this further right now. Yeah. Yes, yeah. We can't make a thread start at main, partly because the signature of main doesn't match what pthread create wants. Pthread create is expecting us to pass in a very specific function signature. And the function signature is that it has to be void pointer return type and void pointer argument. And there's no variation of main within the confines of int main something that will match that pattern. So there's no way for us to really start executing in main. Yeah. Is there any way to know if you are the one true main thread? On Linux, there's a function that's called getTID, which is to get the thread ID. This is not portable. This is not something that's true on other operating systems. This is just a Linux thing. You can ask the question in main before you call pthread create, what is my TID? And then you can use that to decide whether or not you are the one true main thread. On Mac OS, you might just have to have your threads fight to decide which one is the main thread of execution, but generally, though, the main thread of execution is the one that's executing code in the main function. No other thread of execution, like we were just talking about, can run the main function. So we know that the main thread of execution is the one that's in the main function. Yeah. So oh gosh, okay. I hope everyone's having fun with this ride that we're on today. I'm going to make sure I've got UniSTD imported here. My second thread of execution is going to sleep for 10 seconds. I'll make it 5 so we don't have to agonizingly wait for 10 seconds. And my main thread is not going to wait for the new thread of execution that we've just created. So this is before we call pthread create, G, we're done. This is not going to do any more after this. So the main thread here, by returning from the main function, has implicitly called the exit system call. And so the same effect that we saw before with calling exit in the pthread code. Yeah. Yeah. The difference between using threads and functions is that threads are happening at the same time, like air quotes, and literally at the same time when we have multiple cores in our system or multiple processors in our system. If I invoke a function, I'm just adding a new stack frame to the current thing, and I'm only ever going to use one core. If I called pthread create in a loop, it's going to make n threads of execution that are all running concurrently at the same time, as opposed to just calling that function n times. So if I do this like that, and I make this and I run it, we're going to see after I hit H here and press Control D, there's going to be how many lines are there? 6, 7. There's going to be 6 or 7 lines of all of them asking for more input on standard input. So that you can see that they're all printing out here now. They're all running at the same time, and on my system, literally at the same time. Yeah. Yeah.
Wait, so when you call index, does it kill all the threads and then switch up to the
Again, we're asking questions that I don't actually know the answer to. Exec is going to replace our code section. I'm not really sure how it's going to change the actual structure underlying in the operating system in terms of the threads of execution that are running. If we exec to this function, if I exec to the same program, if I exec to the same program, if I do this, and I run threads, so we're in the main function right now. We're blocked right here. I'm going to do Y. The main process is blocked here, waiting for the P thread to finish. The P thread is blocked here on line 19. I'm going to hit K. We print out the value of C is from the child process, or the new thread of execution. Then we've execed the same program. We've replaced this code with our own code section. And the main thread of execution did not return. We never printed out this second line. So now we're back in the main function, and we're kind of starting all over again with no threads of execution. If that with the one thread of execution that is the main thread of execution. Sort of. This is the strangest way to do a loop that I've ever seen, but yeah, I guess so. Okay, all right. This is interesting. This is not what I plan to do today at all, but thank you all for taking me on this ride. What I do want to do is I want to take a look at the actual thread and process control block on the Linux operating system. I want to preface anytime I'm looking at Linux kernel C code with, I am never going to ask you questions about Linux kernel source code. I'm never, ever going to ask you questions about this. My goal for showing you this is, one, this is just a C program that somebody wrote. There's lots of people that were involved in the development of the Linux kernel, but it's just C code. It is just C code underneath. The other goal that I have for this is to kind of take what we've been talking about abstractly in class and like ground it in reality. This is an actual thing that's happening in an actual operating system that is quite possibly running in your pocket or on your machine or somewhere in your life. This code is running somewhere. The data structure that represents threads and processes in Linux is called struct task struct. And I have linked to this up on the course webpage. I welcome you to follow me along with where I'm going in this code if you want to have a bigger version of it in the screen in front of you. But we're going to be taking a look at this on a website that's called the Source Code Explorer. So this link is going to take us to here. This is elixir.bootland.com. And I really like this website because it makes it really easy to explore a code base. We're going to see that as we step through this, it makes it really easy to just like click on the name of a structure and then see where it's been defined in other files. Without having to know what files it's actually been defined in, it's going to help us with that. GitHub has recently added a feature that's like this. On the right side of the page, there's a list of like function names and variables that you can click on to see where those things are defined in other places. But I like this website for that. So struct task struct is defined in this file that's called sketch.h. Sketch.h is part of where the scheduling stuff is built in the Linux operating system. And when we start to talk about schedulers in a little bit, we're not going to come back and see what the Linux kernel schedulers actually look like, but this is kind of the place where we begin to look for that stuff. Task struct is the main structure that represents processes and threads on the Linux operating system. This is the process control block. This is the thread control block for the thing that we've got. The very first couple of things that we can see here, and I'm going to ask quickly, is this big enough for you at the back to see okay? Okay. I can make it a little bit bigger here. The very first couple things that we see are that there's this thing that's called thread info thread info here is a bit of a red herring in the sense that it's not actually about what we think of in terms of our thread's state. Thread info here is a structure that's wrapped with this if def and end if. These are options that you'll set when you're compiling the Linux kernel. There's going to be a huge list of these options that you can set when you're compiling the Linux kernel that will kind of enable and disable features in the Linux kernel. This one is one that's not really related to what we're thinking about in terms of threads, so I'm just going to skip over that one for now. On the next line here, what we've got is this is the state of our thread control block or a process control block. When I type in PS and I see those different states being printed out, this is ultimately the part of the structure that's being referred to here to determine what is the state of this task in the system right now. We're going to ignore this statement right here, and we're going to look at this. Hey, it's our stack. Every task in the system gets its own stack. On Linux, that means that every task struct gets a pointer to its own stack, and that means that every thread of execution gets its own stack. Every thread of execution gets its own stack. So instead of just that one canonical image of here's a stack at the bottom of my address space, now there might be stacks in different locations in my address space because every thread of execution is going to get its own stack. I'm going to keep scrolling down here a little bit, and I'm going to say again that there's lots of these if-def statements here asking if these things have been set at compile time. This SMP option here, this is called symmetric multiprocessing. This is when we've got processors that are all the same on a system. So we've got multiple processors, but they're all the same kind of processor. This is a little different than what we've got with modern Intel processors and like the ARM processors that we've got. ARM processors are not homogeneous cores. They're like, they've got the performance and the energy cores, the energy efficient cores. They're going to have different performance characteristics per core as opposed to being the same for everything. SMP effectively means that they're all the same type of core. They're all the same type of structure. I'm going to keep scrolling down here, and I'm going to skip past a lot of this stuff because it's way outside the scope of our course. But the next thing that I want to take a look at is on line 956. On line 956 here, this struct here, this structure represents a reference to the address space for this task. So each of these task structs are going to get their own stack variable or their own stack pointer, but all of the threads of execution that are within one process, they're all going to point at the same virtual address space here. When I do a fork, when I do the clone that's not causing me to use the same virtual address space, we're going to get a different pointer to a different virtual address space. But in terms of the threads of execution that we've got, that pointer is going to point at the same virtual address space for the multiple threads of execution that we've got. We're going to keep going down here to line 1055. And on line 1055, we have an interesting friend here, which is our process ID. This is the ID of the task. When we call getPid, this is the value that we're getting out of getPid. On line 1068 plus here, we're starting to see references to the task that created us, who was our parents. We're starting to see references to the children processes that we created. So the other processes that we created when we called fork. I'm going to keep going down to line 1183. Way down here. And here, we've got a reference to a structure that is our open file table for this thread control block, for this process control block. We've got signal handlers here. And I'm going to go way, way down. I'm going to keep going way, way down. I'm going to keep going way, way down. I'm going to keep going down. Just keep going down. I don't know if you're counting how many lines of code this struct is, but it's many hundreds at this point. I'm going to keep going down, way, way down to the very end of it. Here it is. So we started at line 813, and now we're on line 1664. So this is 800 lines long. This is 800 lines long. The really important part that I want to stop at here is this. This is our context. This is our processor context. This represents the state of our processor as this task is being taken off of the CPU and the state that we're going to put onto the CPU as we're going back onto the CPU. I'm going to open this link, and what this link does is it will take us to all the places where it has been defined, where this structure has been defined. Every place where this structure has been defined is in a folder that's called Arch here. This is for architecture-specific stuff in the Linux kernel. Architecture here being x86 or ARM or MIPS or M68K. I'm surprised to see this here. This is like, you know those really old Macintosh computers that have the little screen on the front of them? That's a 68K processor in that. There's OpenRISC, there's LunarCh, there's Spark, there's x86. Let's click on x86 here. This is the structure that represents the registers on the CPU. Here is our stack pointer. That's awesome. Every one of these architectures is going to have their own structure defined for this context. Every architecture is going to have its own different kind of structure defined for this context that represents the state of the processor. And that's a stack pointer. I think that's awesome. I think that is so cool. Heavy emphasis on, I'm never going to ask you questions about the Linux kernel on a test, but I think this is awesome. I think it is really cool to be able to see that this is what's actually being used by this operating system to represent the state of a processor on the system as we are doing context switches. This is that idea materialized. We're going to populate this structure and put it into this process control block as this is coming off the processor, so that when I put it back on the processor, I'm going to be able to get to that same state that we were in before. That's the end of my spelunk through the Linux kernel itself. And I think it's really cool to be able to see that. Tomorrow, what I want to do is spend some time with some critical sections. And I want to draw your attention to the chapters that are in the textbook that we're taking a look at for this part of our course. The two that we're taking a look at for this part of our course are chapters 26 and 27 here. Chapter 27, I'm going to emphasize, is mostly about what we've done live and in person today. It's taking us through the API that's used for creating and managing threads. So this chapter is much more of a reference in terms of the kinds of functions that you can use for working with pthreads than it is for anything else. The part that we're going to be spending time taking a look at tomorrow is specifically in this chapter, where we're thinking about the idea of concurrency, and then the keyword that we're looking for here is critical sections. Critical sections, and I'll give you a brief introduction to this idea to help prime you for this. A critical section is a piece of code or a section of code that contains something that's called a race condition. And a race condition is where we've got multiple different concurrent actors. So here I'm trying to say two different threads of execution, trying to make changes to the same variable at the same time, approximately at the same time. So like air quotes at the same time or literally at the same time. We'll take a look at some code samples tomorrow. We'll identify whether or not there is a critical section in this code, and then we're going to try to fix that critical section using a structure called a lock. So at this point, you should be able to compare and contrast processes, threads, and applications. You should be able to have some idea to describe the relationship between a process and threads of execution within that process. You should be able to explain some of the differences between processes and threads. You should be able to write code that uses library calls to create and manage threads. So you should be able to do pthread create, and you should be able to do pthread join minimally here. And you should be able to describe some of the operating system data structures needed to manage a process and those needed to manage a thread. So you should have this idea of a process control block. You should have this idea of a thread control block, going back to things like context, stack pointers, that sort of thing to represent tasks. That's it for today. I hope that you have a great rest of your day, and I will see you all tomorrow. Bye, everyone.